Regular computing is pervasive in our modern society. The devices in our hands, in front of our faces, powering our careers, they all mean a lot to us, and are built on the foundations of computing stretching back several generations. However, the world isn't simply black and white, but it isn't different shades of grey either. We live in a multi-dimensional analog world, and converting the analog to digital seems today very easy. The next step in our computing adventure is quantum computing, and before you switch off because it's not here yet, I'm here to tell you actually it is. Today you can book time on a quantum computer for free and run quantum simulations. The question of quantum computing is a matter of scale. Think of it like an add-on to traditional computing, and the results from this new type of accelerator could enable new insights into physical compute problems, such as protein folding, optimization, and security. IBM Research sponsored this video and took us to see their latest SystemOne quantum computer and how one of those super cold refrigerators are put together, and some detail on their 180 plus collaborations in quantum computing and research around the world. What's your minimum specification? So to begin, let's bring everyone up to speed on the raw basics of quantum computing. Traditionally, we see the world in an analog form. It isn't black and white, but various shades of grey, depending on your outlook. For modern computing, we convert that into digital signals, either on or off in something called a bit. If you want something more nuanced than a 1 or a 0, we use multiple bits to simulate an analog response. For example, the colour you're seeing me in now is composed of red, green, and blue, where each of these colours can be one of 256 intensity states. When paired together, your brain sees a combined colour, such as yellow or purple, based on the digitization of colour. Quantum computing brings us back into the analog realm, but instead of going between black and white in shades of grey, colours can be combined together at once, and going between black and white means going through all the spectrum at once. A quantum computer takes the combined analog signal equivalent of multiple pieces of data at once and puts it into a qubit. Put enough qubits together, and you can design a program that will allow you to get the result. The downside is that you also have to get the answers. You also get the answers that you don't want, so you have to build a program that gets rid of those. Simply put, if the world is in analog and computers are digital, then quantum is analog evolved. It makes the topic very complex to talk about, let alone discuss in a video format such as this. But that's not to say it's impossible. If you follow quantum computing, you may already know that there is 25 plus years of history behind it, and it might be 10 to 25 years before it becomes useful. It's one of those in 10 years technologies that always seems to require another 10 years. But nonetheless, the researchers here at IBM are focusing in on their flavor of quantum processor that they're already making available today for use on their cloud platform. And yes, I did say there are flavors of quantum processor. Not only can I wait to try them all and tell you how they taste, but it's clear that some have more benefit than others. So my first stop before hitting the labs was a chat with Dr. Dario Gill here at the Yorktown facility. The quantum research at IBM has been here long enough to have some interesting items of quantum development history. So what makes quantum computing appealing, as a foundation for research?
What I am most excited about is that it is the first time in the history of computing, with a capital C,
right,
that the category itself is branching. So I think what is appealing is that it's a refoundation of the fundamental ideas of what is information and how do we compute. And something that exciting and profound has to be explored. So I think that's what's so exciting, a new way to process information, a new way to compute.
Well, so along those lines, what will quantum computers be able to do that traditional computing can't?
So there are problems that we have in the world that cannot be modeled effectively or calculated effectively with classical computer. A whole class of them are modeling the natural world. We know that the physical world obeys the laws of quantum mechanics. So if you want to solve problems in physics, in material science, in chemistry, right, even in the life sciences over time, all of those things, if you want to model them with sufficient accuracy, let's say you want to build a better battery technology or a better fertilizer or a better catalyst for an industrial process, quantum computers will be able to make a difference over time in all of those problems. The second category is there's problems in mathematics of data that has structure that also can be mapped to quantum computers with great efficiency, exponentially faster than classical computers. Factoring, which is used
the classical
for cryptography, it's a very famous example, but there are other problems in machine learning and finding, structuring data that is also will be relevant. So those are the two big categories.
One of the key aspects of quantum computing is the temperature. In order to exploit the nature of these quantum systems, we need to go as cold as a thousandth of a Kelvin, which is around negative 459 Fahrenheit or negative 273 degrees Celsius. In order to get there, we need a very powerful fridge, which the industry calls a dilution chamber. IBM calls it their quantum chandelier. Dr. Chow, IBM's Director of Quantum Infrastructure Development, took me through this marvel of precise engineering. So here we have the dilution chamber, quantum chandelier, and joining me is Dario Chow, going to take us through this. So tell me, what exactly am I looking at? Right, it looks like something my nan might put on a ceiling.
Yeah, exactly. We certainly call it the chandelier.
Yeah.
But actually, this is the inside of one of our dilution refrigeration systems that cools down our quantum processors, right? And so we work with superconducting qubits, right? So they need to be extremely, extremely cold to work, right? They basically need to be at 15 millikelvin, right? So 0.015 above absolute zero.
15
millikelvin.
15.
Yeah.
Okay.
And if you think about, we always call it colder than outer space, right? Think about the depth of the space. It's the cosmic microwave background.
It's about 4 Kelvin, 3 Kelvin, yeah.
Right. So orders of magnitude colder than it is in space.
So, but nothing's colder than space, right? Right. Oh, I guess we're using physics here. Right?
Exactly. I mean, the cooling technology down to temperatures this low has existed, for quite some time.
Right.
But what's been tremendous about this type of instrument is that it's effectively turnkey, and it can cool down to these types of temperatures without us actually filling it with any sort of liquid cryogens.
Right.
Yeah.
When I first came in, before we started filming, I saw these massive copper wires, and I thought, oh, you must have some high-powered current in there. But you were like, no.
Yeah, no. So I mean, a lot of these are just for heat sinking to these. We call them cold heads.
So you got one that side, one this side.
Yeah, and these are the systems with the pulse tube in them that actually has this closed system of helium, and that's what gets this plate that you're looking at here to 4 Kelvin.
Okay.
So all these different plates are actually at different temperatures.
So you've got determined thermal zones, one here, one here, one here, one here, and you're decreasing as you go down.
Exactly. You got it. Yeah. So room temperature, around 50 to 60 Kelvin, 4 Kelvin, 800 millikelvin, 100 millikelvin, and then 15 millikelvin. The second stage refrigerator is here. It's called the actual dilution refrigerator.
Right.
And it's what gets us down to that lowest temperature for the quantum chip that sits all the way at the bottom.
Oh, wow. Okay.
Yeah.
It's I don't know what I was expecting. Maybe something smaller, maybe something bigger. I don't know. But obviously, you've got lots of cables coming out here. Are these for extra cooling, or are they the control electronics?
Exactly. The cables are actually for the controls, right? And so what you're looking at here with all these different cables that come down.
Oh, the loops of the cables. I thought they were to do with the refrigerant. Okay.
Nope. So these are bringing the signals, both your inputs and your outputs, to the actual quantum processor. When we program a quantum processor, you're effectively sending microwave pulses from something at room temperature. It's controlled at room temperature down through these different cables to interact with the qubits that are in the chip.
When you say microwave pulses, are we talking about microwave frequency or microwave?
You got it.
Energy.
Microwave frequencies, pulses of lengths between tens of nanoseconds to hundreds of nanoseconds.
Right.
Sitting at 5 gigahertz, 6 gigahertz, depending on the qubit frequencies and depending on the architecture that we have in the chip.
So your qubit is controlled by a 5 gigahertz system, just to relate it.
Yes. And a lot of the infrastructure for the control sits at room temperature. What you have inside the refrigerator are more of you can think of it as the cryogenic peripherals to condition the pulses, to make sure that they're at the right signal levels, that they're at the right noise levels, and that the signals that come out are amplified to the right degree.
So this is the motherboard.
You can think of that way. I mean, certainly you can think of it as the backplane supporting the actual quantum chip, right? So you have all the
backplane,
right, and all the other pieces like there's filters, there's other passive microwave components, there's certain active microwave components.
Microwave filters, right? Okay, for the
signals. Yep.
Yeah.
Yep.
So I've noticed that all of these sections, you've got circular, but they're in a decreasing radius, right?
Yes.
But the
Yes.
but the refrigeration we see is typically cylindrical, right? Not conical.
Yeah, so actually
Is
what
there a
you're
reason
looking
for
at
that?
is every one of these plates, which we've already said is at a slightly colder
Yeah.
temperature, that we enclose them for radiation purposes. And so the lower one is enclosed with a cylinder that's that's of that diameter, and then one that's slightly larger, one that's slightly larger, and then the whole thing is closed up. And from the outside, you just see the outermost cylinder.
So even with this engineering feat to get this far at these temperatures, one of the critical points of quantum supercomputing is the software behind it all. Not only software to control it, but these are still computers. You need to run computer code designed for quantum systems. This requires a bit of brain breaking to understand. IBM's latest quantum computer is called SystemOne. Programming for it is not like standard computer code. First you have to design your quantum circuits called primitives, and then push the code through the circuits. So this is what, a third gen? Do you classify them in generations like that?
So I mean, effectively, a lot of what you see in here is part of what you might see in a quantum system 1, right?
Okay.
The quantum system 1.
I think we're going to go see one
we're
later.
Go see one of those, right? And it effectively, allows us to control the number of qubits up to 100 or so, right?
Okay.
So our latest Eagle processor is still in a quantum system 1.
But then you've got 433
We've got
here.
433 planned and 1,000 plus planned with Condor, and
So I
whole
guess you're in
roadmap beyond.
deep research into what is needed.
Yes, right. So I mean, it's certainly going to be an evolutionary path of the cryostat and the cooling as well. We actually have a partnership with Blue Force, which is one of the vendors of these systems. These cryogenic systems, to look at what larger pieces of cooling might look like, to effectively support some of the systems that we're building towards. And we've been doing some internal research as well to develop better cooling methods and larger fridges and so forth.
While I was on site, IBM gave me an insight into the programming, but also let me construct the dilution refrigeration casing around one of these systems.
In order to get the fridge really cold, it works kind of like a Russian nesting doll, where there's multiple layers of vacuum. Kind of like in your coffee cup, your coffee mug, you have a vacuum layer on the outside that prevents the heat transfer. And then we do the same thing here, where you have inside this one, there's another layer, and we're going to build up layers just kind of like a Russian nesting doll. So we put on this, and in between here, when we pull vacuum, it will form a barrier for heat transfer. And then each layer progressively gets colder and colder, all the way down from room temperature, all the way down to 10 millikelvin.
So like a thermos, keep hot things hot and cold things cold.
Exactly.
So you're just doing maintenance on these, or is this construction?
We did some maintenance, but also we're swapping samples,
Okay.
putting new qubit samples in.
Okay.
And these smaller, you see the bigger and smaller fridges. The smaller fridges, we're studying single qubits,
right.
and there they study multi-qubits.
And they can measure hundreds of these qubits.
Yeah. There's 240. I just put 240 new qubits in here,
Okay.
but they're not entangled
They're not all
or anything.
coupled,
Okay.
but they allow us to test for new features and new, characteristics to improve them.
But how do they taste?
I have not tasted them yet.
Don't lick
I
our
don't
way
think I
first.
will.
Almost all the developers I know think in a very digital way, because that's how they've been trained. Writing the same program for a quantum computer is difficult because you're in a multi-dimensional analog space. This means quantum computers are currently aiming at problems that map to that scenario, such as molecular dynamics or cryptography, and the holy grail of next stage of quantum computing, or what IBM calls the quantum advantage. You talk about quantum advantage. So what does quantum advantage mean to IBM?
Well, quantum advantage, I wouldn't say just to IBM, to the field overall, because it's a very widely used term, means the moment where we can solve a problem using quantum computers that make it either faster or cheaper than you could do with a classical machine. And the problem has to have some practical value.
Right.
Right? It has to be something that either helps us better understanding in science, or deliver business value. That's the term of advantage.
It can't simply be arbitrary.
Yeah, because I think, in contrast to some other terms that have been used before, the problems have of no practical value.
Right.
So then that's like less exciting, I think.
So I think a key question is, when will we get there?
Look, it's going to happen. That's a very important question, very often asked, but it is definitely going to happen this decade. And in fact, we're working very hard to do the first demonstrations of quantum advantage in the coming years. Whether is it 2 years, is it 1 year, is it 3 years, but it's definitely happening this decade. And it's likely, if I were to assign a probability distribution, I would say, reasonable probability that this will happen in the next few years, a first demonstration.
Also on the software story, let's talk about the issue I mentioned at the beginning. Will quantum computers be able to break the encryption to read all my cat sanctuary emails? I've been speaking to IBM experts on this, and the reassuring answer is probably not. The reason is because the community is aware enough of the potential power that quantum computers can have. With enough qubits, you could arguably simulate pretty much everything, but by the same token, you can also design around it. One of IBM's focus points here is the development of quantum-safe technologies, which also includes cryptography, such as algorithms behind security that aren't simply a global search space solution, but require some actual smarts in the code. You may have heard of asymmetric cryptography, which follows along similar lines. IBM has a good number of projects in this space, which you can read more about on their website, which has more content put on it regularly, especially for those interested in getting to grips with these problems. A number of the solutions here end up being collaborations with IBM's partners. Aparna Prabhakar is the VP in charge of IBM's Quantum Partner Analysis, and I got a chance to ask her a few questions. This isn't just IBM doing quantum, and so I kind of want to get an idea of how many partners you have and what verticals they play in, right? It's people very easy to see quantum as this sort of like individual one spot in space, but can you kind of put the other spots in and draw a line for me?
So today we have around 180 plus partners, and they are spread across 6 continents and come in different shapes and sizes. We have around 40 startups in our ecosystem. We have 18 GSIs across the board. We have 7 ISVs who are traditional software vendors who are working with us and integrating to their workflows. We have academias, and then we have huge national ecosystems which we are building. As an example, we are building a national ecosystem in Japan where we are working with University of Tokyo, University of Kyoto, engaged with the government to really push the ecosystem on 4 key dimensions. One is on research and development of quantum as a strategic industry. Second is actually creating a supply chain which is essential to how quantum will progress. Third is actually creating the workforce, because quantum is coming, but there are not enough people who are actually quantum educated and enabled. So we are working with our partners to create those workforce development. And the last one is really for those people who don't want any of this and just want to use quantum computing as a tool. So we are enabling and getting quantum computing as a tool out there so that more and more people can get hands on the keyboard, because there's so many unknowns with quantum that you don't know what you don't know. And that's where partners come in, is they are working with us to really identify those unknowns and work with us to really break the boundaries of what we know today.
One thing that interests me is whenever we talk about something more commercial, you have customers and you have partners. Some of them are ready to go day one. They've done the research, they've done the due diligence, then they're ready to move forward. Others are kind of thinking about it and they kind of go into the unknown, right, with almost zero knowledge, right? Mm-hmm. So can you give me a sense of your partners? Are they all up to speed when you start engaging with them, or do you find that you have to kind of lead them along the way, or?
Actually, that's what I love about quantum ecosystem, is there is no set recipe.
Yeah.
At one end of the spectrum, you have these folks who are quantum native, and I would say only 20% or so of our ecosystem is actually quantum native. Those guys who are actually writing Nature paper, who already know the experiments they want to do. And then there is a fair amount of, I would say 30% who are like, hey, quantum's coming. Tell me more about it. What is this like shiny thing? How do I make sure that I'm right there ready to go? And then there is a bunch of folks who are in middle who are not like what you would call the most advanced, but who know enough to start experimenting and who are sitting in their domains and saying, okay, we understand our domains really well, we understand quantum really well, but we don't exactly know how to integrate these together. So I think there are three categories of folks: quantum native, quantum newbies, and folks who are exploring quantum, not in either of those buckets.
Do you have any partners that are currently able to monetize their quantum vision right now, or is it still just primarily research into finding the right level of integration?
I think there are yes, and there are startups who are actually monetizing as of today.
Oh, wow.
And those are startups who are actually building and exploring use cases as an example with some of the enterprise. So they are working with large enterprises.
Yeah.
They are looking at their use cases and figuring out how to translate that into quantum speak. That's one element. The second set of folks are academia, who actually are operating as our hubs. So they get access from us, but they really want to reach out to a broader community, and that's our play here. We really are thinking about scale, and they are then reselling that access alongside education. A great example of this is Fraunhofer, a huge partner for us. They are our system partner as well. But they are not just reselling access, they are educating the entire human workforce and enabling that as well. And they are making money out of it.
So IBM isn't the only player in town when it comes to the quantum hardware and the quantum stack, and we see in other communities the push to be open and have open standards and that whole support. Are there room for multiple players in this space to either be competitors or to collaborate together?
And the answer is yes. So I think this is going to be a competition for a little bit. And I would say IBM is far ahead of others. But let's talk about this a little bit. So the short answer is yes. In near future, I see a world where different technologies will coexist till there are clearly defined use cases and value capture which will happen. I think we are about a year or two away from there for that to happen. Now, I'll give you an example. Recently, IBM has chosen to do minority investment in Quantinuum, which is an ion-based company, which was merger of Honeywell and CQC. And the reason why we did that is because we was thinking about our clients first. Today, even though IBM is ahead in terms of its roadmap, in terms of like showing leadership where we are, the clients really want to explore with optionality. They want to think about building things which are modular in nature, which can be abstracted, which can be thoughtful around the way. And what we are doing with these partnerships is ensuring that from a client perspective, we are really putting the client first, and we are setting the right standards across the industry, speaking the right language, and talking about the same things across the board. And that is where the collaboration comes into play, is setting those standards, foundations, and the right language, which becomes the common ground on which the rest of us are building up.
Do you find that partners are aligning their quantum roadmaps to yours? Because obviously you have multiple generations of product in the pipeline, and IBM's launched its roadmap. And in other industries, we find that, especially for commercialization and monetization, people have to align when their product comes out with when their partner's hardware product comes out. Is there any of that going on right now?
I think what I see happening is our competition is adopting a lot of metrics from us. So for example, the quantum volume, which is our metric of how quality, how good the qubits are, was adopted by ion-based system and superconducting as well. The clops, which is what we put out, how fast do these quantum circuits run? We put it out last December, and that got adopted by Rigetti as an example.
Yeah.
And before that, remember, there was no way to talk about how do you think about the number, the quality, and the speed. So we do see that as an adoption metric. Second is Qiskit by itself, and Chasm 3 is one of the most broadly, I think we are 10x ahead of anybody else in terms of adoption. On the Chasm 3 steering committee have AWS, Microsoft, and University of Innsbruck sitting with us and helping us define what that open source Chasm should look like. So there's a lot of that moving ahead. From the roadmap, we are the only ones who have delivered on the roadmap consistently as we've spoken about it. And when you look at our roadmap, some would call it really ambitious. We call it safe. So I don't think others are there as yet to really talk about that far ahead because they are not advanced in true sense as the way we are.
That's a fundamental key point here, roadmaps. If we talk about a CPU roadmap or a GPU roadmap, we talk about an architecture, a microarchitecture, a design, production, time to market, pricing, performance. That's on top of all the research and development, which can take 3 to 5 years depending on the project size, the funding and the capability, and the demands of the design team. The question is if quantum computer roadmaps look similar to CPU roadmaps, or should we look at them differently? Give us an understanding of where IBM currently sits in its quantum roadmap.
Yeah, so we have laid out this quantum roadmap. We've shared it, over a year and a half, and we've extended it this year. So let's break it down into pieces. One piece of it, think about it as the hardware element.
Right.
Can you make better quantum devices? Can you make a better quantum processor and the packaging?
Bigger ones of these.
Bigger ones of these with more qubits and so on. So where are we right now? So last year, we were the first company in the world to break the 100 qubit barrier. For superconducting technology, so we built a system with 117 with a processor called Eagle. This year, 433. Next year, 1,127. After that, we laid out our roadmap. By 2025, we will have systems with at least 4,000 qubits. And the important element of that is to parallelize things, modularity, multiple quantum processors connected to one another. If you look above that stack, is the whole software enablement stack. So we've made massive progress around the kernel, like the low-level programming, assembly language equivalent, and that is with Qiskit runtime. And above that is the algorithmic effort around more classes of algorithms for machine learning, as an example. And then for model developers, which is you're raising the level of abstraction enough that anybody can sort of just call a primitive or something to run on your Python program. You don't need to know any quantum physics, and you benefit from quantum, right? So the stack is both make the machines better and make a whole software enablement stack and an ecosystem to allow, a frictionless use of quantum computers.
So does that mean when we get quantum libraries, the adoption has the opportunity to
explode?
Expand,
yeah. I mean, the ultimate vision is I think there's something like 20 million people that earn a living writing code around the world.
Right.
So the broad vision would be that behind the scenes, on every software program that is run, there are things behind the scenes, not everything, there are things around that are running on quantum machines. And, look, we've seen a parallel to that with AI, right? We've gone from having very deterministic programs around that once we wanted to learn from data, we've seen more and more elements within the software we all write now have an element where you are using neural networks and special accelerators behind the scenes around that. So you can imagine sort of like that evolution where the future of software will be the combination of exploring these high precision computation, the neural networks, and the quantum processors, all kind of in a transparent fashion.
So it also sounds like at the right time that comes along, you also need all the software engineers, to be ready to compute for either quantum or use the libraries. So this means outreach into academic, not only at the lowest level, but also at the high software level. But I speak to people in those fields, and quantum computing, it's maybe a briefest mention or it's a specialist module. There's got to be a time where quantum computing becomes a fundamental part of a CS or an EE degree, right?
Yeah, I actually think that's one of the most exciting things going on right now, which is there's a massive interest of the next generation, let's call it the quantum native generation, to learn about the concept, to write their first programs, to delve into how do you write a program, the algorithm piece of it. Some people are fascinated by the technology itself and how you advance it. So let's give some figures around that. So online education, we provide lots and lots of support through YouTube channels, and like we have an open source textbook as well, and through Qiskit. So 3.5 million learners online learning about quantum already. You are also seeing, I mean, to give you another figure of merit of interest of students, we have a summer internship program that we run here in IBM Quantum and IBM Research. And we take about 60 students for the quantum program. Last 2 years, we've received 15,000 applicants.
Even during the pandemic?
Even during the pandemic.
Wow.
So what that tells us, and you're starting to see in the universities, everybody's starting to develop what you mentioned, the curriculum. We've also developed certification for developers. So this is going to be the beginning of that journey, but I would say is the equivalent of what was happening if you were in 2012, right? Around that time, in universities around deep learning, as an example. It was just the beginning. You fast forward, and there are some of the most popular classes in all the,
I did CUDA in 2010, right? It's that sort of time scale, I guess.
So, but I mean, it's like, sometimes it's challenging to do these perfect analogies around these things, but it is the beginning of what you're seeing around that. But I think my prediction is like, within this decade, there will not be a computer science, program anywhere in the world that does not include now elements around quantum information and quantum computing. It'll be an element of the curriculum, but I think that's what we're going to see.
We were talking earlier about the fact that IBM already has quantum computers in the cloud for people to use, and you were showing me some really impressive numbers.
Yeah.
Can you go over what some of those numbers are?
So look, we have at present over 20 quantum computers available on the IBM cloud, that some of them are totally free and available to use for anywhere in the world to learn, right, and write their first programs using quantum computers. And then we have a whole other set of quantum computers that are in support of the IBM Quantum Network. So what are some of the numbers around that? Every day, there's 3.5 billion circuits, which are sort of the primitives behind these programs, that are run on IBM quantum computers. So real quantum hardware with quantum programs run, 3.5 billion. Cumulatively, since we put the first system on the cloud in May 2016, over 1 trillion circuits have been run on quantum computers. A community in terms of users of the IBM Quantum Network, close to 500,000 users all over the world. We have 180 plus institutions, from national labs, startup, universities, Fortune 500 companies all over the world that are also using quantum computers. So it is like an exponentially growing community that are learning, do an R&D. I'll give you another statistic. Over 1,000 scientific publications have been generated using IBM quantum computers. So it's just a vastly growing community, and that's exciting to see.
So one thing I wanted to broach was cost, right? We're still in a very early research phase, but we've seen other sorts of more traditional computing, I guess, be really expensive, miniaturized, and now I've got a smartwatch and a smartphone, and people want to wonder, is quantum computing, going to come to those sorts of devices, right? In the cooling you need, maybe not, but what's the vision here?
So the vision, it's people will experience the benefit of quantum computers, and I think that will be quite universal, right, through the end results that it generates. But they will be used in a cloud fashion. I mean, and whether it's on a public cloud that you pay per, circuit that you run, or you have dedicated systems, right? Using the most modern software stack because you have a very high utilization environment, and that's more cost effective than running per circuit. We're going to accommodate all of those models, and we're seeing all of those models being present. So we have a cloud delivery that you pay per service, and then you have centers like we have at University of Tokyo or Fraunhofer in Germany, where they have traditional computing environments, and it says I want my own quantum computer because I'm going to consume all of it on Plus. So we're going to see all of that, but do I envision that people are going to have these things in their home? No, not anytime soon. So, but I think we're all accustomed to the idea of you have your local terminal devices, your phones, interfaces, and behind the scenes, the cloud is supporting you. So this will be the model for quantum too.
That's great. Thank you.
Thank you so much.
So a big thanks here to IBM for inviting me to tour their quantum research facility here in Yorktown in New York State. I've been putting together my first quantum system, or at least the shells, and I didn't split the world in half, so with any luck, we're all still good to go for the next generation of quantum computers. If you're interested in what IBM is doing here with quantum computing, But also, if you feel like a job at quantum computing is in your future, then there will be a series of links in the description below. At the start of this video, I spoke about the flavors of quantum computing. My minimum specification here is that at some point, I'd like to try them all.